Thank you, Palona, for the opportunity. So today I'm going to talk, as Palona said, about the weighted inequalities for Calderon-Zygmund operators. The start of this talk is going to be a little bit of motivation and some definitions concerning this, and then I'll get into the main results and some extensions that come into this area. Okay. So I'll start with the definition of singular integral operators. The Calderon-Zygmund operators fall into a subclass of these operators. So what we are going to see today is a lot about the weighted inequalities for these singular integral operators. So singular integral operators are integral operators that are associated to some kernel that barely or sparsely fails to be integrable along the diagonal x equal to y. A canonical example of this is Hilbert transform, which we denote with this symbol h. So for some nice function f, the Hilbert transform is defined as this principal valued integral. So what we mean by the principal valued integral is, if you look at this integral, there is a problem in the domain of integration. So instead of considering this as an integral operator, we write it down as a limit of this sequence of integrals where we change the domain to remove the point of singularity. So that's how we define the Hilbert transform of a function. So there is a lot of motivation towards studying the weighted inequalities for these operators, and we'll specifically look at some of the applications of the Hilbert transform and some other examples of singular integral operators that make use and understand why we studied the weighted inequalities for these. So for the Hilbert transform, it has many interesting properties, and I have just written a couple of these here. Some of this includes that the Hilbert transform commutes with translations, complex conjugation, differentiation, and positive dilations. It's also interesting to note that this is an isomorphism on L2 of R, and if one was to look at the inverse of Hilbert transform, it's actually equal to minus H. The Hilbert transform is also bounded on LP of R for P lying between 1 and infinity, and the Fourier transform of Hilbert transform of function is given here in terms of the sine function and Fourier transform of this function f. So as to the applications of why this operator is interesting, I have listed a couple of reasons for that. The LP boundedness of the Hilbert transform implies the convergence of Fourier series of a function on the LP spaces for P lying between 1 and infinity to f in norm. So this is one very interesting reason of why this operator is very interesting. And another reason is concerned with analytical functions. So if we were to look at the boundary function of a harmonic function on the upper half space, the Hilbert transform actually maps it to the boundary function of its harmonic conjugate. What I mean by that is, if you consider a function f, which is holomorphic on the upper half space, and it has some decay, then imaginary part of f is the Hilbert transform applied to the real part of the function. Now I'll give you another example of an interesting singular integral operator. As expected, this is the Riesz transform, which we can consider as an n-dimensional analog of the Hilbert transform. For j lying between 1 and n, the Riesz transform, which we denote here with Rj, is defined as this principal valued integral. Riesz transform 2 is very interesting and has many interesting properties, and I've tried to list a couple of properties here. So for functions on the L2 spaces on Rn, the Riesz transform gives this beautiful inversion formula. What this formula is if you look at the Rj squared applied to f and sum for all j lying between 1 and n, then this summation actually equals negative of f. So this is the inversion formula. Riesz transform also makes its applications in differentiation by actually giving us information about the Hessian of a function. given that we have an information about the Laplacian, so that is summed up in this equality that you see here. So we consider a function u, and we look at an element in the Hessian matrix of u, and that is just Riesz transform applied to the Laplacian of u. And here j and k lie in between 1 and n. So these are some of the reasons why these operators are interesting. Now, what we are going to look at today is concerned with the weighted inequalities for these operators. So I'm going to start by defining what a weight is. A weight is a non-negative locally finite Borel measure. So as a simple example, we can look at the Lebesgue measure. Okay. And here I've written down some of the motivation behind the study of the weighted inequalities for singular integral operators. So it so happens that these weighted inequalities come up naturally when one looks at the Toeplitz operator theory and in the spectral theory of Jacobi matrices. This also appears in the operator theoretic questions, such as when one is interested to look at the subspaces of Hardy space that are invariant under the inverse shift operators. This translates itself to two-weight inequalities of the Hilbert transform. So this is a little bit of motivation. In this talk, I'll also give a little bit of description on not just the two-weight stuff, but also the multi-weight inequalities for multilinear operators, multilinear singular integral operators. And these were introduced by Koifman and Mayer in their study of Calderon commutators, pseudo-differential operators, and paraproducts. So the kind of questions that I would be concentrating on would start with the inequality described by 1. So what we consider is a weight u. And the question that we are looking to, that I'm going to describe here today would be of this form. So I'm going to show you some characterization for a weight such that the singular integral operator t bounded from L to U is bounded from L to U to L to U. So that's summed up in this inequality that you see here. Where n can be understood as the best constant or the operator norm of t. So here what you see is a description of a one-weight inequality. What I am going to discuss a little bit later is the two-weight inequalities, but I'll start with describing the one-weight inequalities. So for this one-weight inequality, there are several solutions for singular integral operators, but I would be concentrating a little bit about the case of Hilbert transform and give you two different solutions that have been proposed in this case. And the first solution about the characterization was provided by Hilson and Seko. And in this characterization, we characterize the weight u that satisfies the one-weight inequality that was described in equation 1 using these functions w and v that are L infinity functions. And h here is the Hilbert transform. The L infinity norm of v is less than pi over 2. So this is one of the characterization for the one-weight inequality of the Hilbert transform. Another very known characterization is Hunt, Muckenhaupt, and Whedon characterization in terms of the Muckenhaupt A2 weights. So in this characterization, we see that the weight u satisfies the one-weight inequality described by equation 1 that we've seen earlier for the Hilbert transform, if and only if u is an A2 weight. Now, what it means to be an A2 weight is described in this equation here. So if we consider w of x as u of x raised to the power of -1 or 1 over u of x, this is the A2 weight of u or the A2 norm of u, which is the supremum over all intervals I in R. This quantity is finite. We say that u is an A2 weight, and this is a characterization that u needs to satisfy for the for the one-weight inequality of the Hilbert transform. It's very interesting to note that these characterizations offer a very different perspective for the weight u, and there is I do not know of any way to get from one of these characterizations to the other. So it's a very interesting description of weights. So the kind of question that we were interested in resolving includes two weights, u and v. And the question is if we can provide a set of necessary and sufficient conditions on these weights u and v so that the two-weight norm inequality described by equation 2 here holds for a singular integral operator t. Again, here n can be understood as the best constant or the operator norm of t. In order to resolve this question, the NTV conjecture was proposed by Nasrov, Trail, and Wahlberg. And this was about providing the real variable characterization for the weights u and v. So t is bounded from L to u to L to v. This conjecture took a lot of time to be solved, and it was solved recently for the Hilbert transform. And this was supplied in two papers by Lacy, Sawyer, Shen, Uriarte, Toero, and Lacy. And here is the solution that was proposed for the two-weight inequality of the Hilbert transform. So suppose that, so the solution is as follows. So we consider these weights u and v, and we suppose that they do not share a common point mass, which is described here. And we assume that these weights satisfy the equation 3 and 4. Equation 3 is what we call a full Poisson A2 condition. Equation 4 is called testing conditions. So if these are satisfied, the two-weight inequality that was given in equation 2 holds as long as these conditions are satisfied. It was also that they characterize the best constant in the two-weight inequality in terms of the A2 constant and the testing constant that you see in the equations 3 and 4. So a little bit about the conditions 3 and 4. So condition 3, as I said earlier, is called a full Poisson A2 condition because PUI that you see here is the Poisson integral associated to the interval I, which is described as this integral with the distance function. And the condition 4 that you see here are called the testing conditions. These were originally introduced by Eric Sawyer for giving a characterization of these weighted inequalities for operators with positive kernels. So this was the characterization provided for the two-weight inequality of the Hilbert transform. The restriction that you see regarding common point masses that is described here was resolved by a result of Heitinen. So it was removed, which strengthened this result. And after this result came up, there were several other results given for some other canonical operators, such as the Riesz transform, Cauchy transform, and the Bergman projection, under some additional assumptions on the pair of weights. So the two-weight results for Riesz transform, I've only listed a few of them here. So the two-weight results for the Riesz transform and fractional versions were given by Lacy Wick. Some were given for the Cauchy transform by Lacy, Sawyer, Shen, Uriarte, Toero, and Wick. And for Bergman projection, Fang and Wang using the notion of doubling measures. So I only listed a few. Our work began to resolve the NTV conjecture in an attempt to provide a set of sufficient conditions on the weights u and v. So the two-weight norm inequality given here holds for Calderon-Zygmund operators on the setting of spaces of homogeneous type that we have described here as a tuple xt mu. So our work concerns providing only the sufficient conditions because we were dealing with a wide range of operators on space of homogeneous type. So a little bit about space of why we choose to work on this. So space of homogeneous type is where we don't really have the group structure. There's no Fourier transform, but the harmonic analysis extends beautifully. And we started working on Euclidean spaces and quickly realized that we could give a generic result on the space of homogeneous type instead. So that's where our result comes. So since we are working on space of homogeneous type, I thought we would describe and define this space of homogeneous type. So let me define that. So the tuple xt mu is called a space of homogeneous type if D is a quasi-metric and mu is a non-zero measure that satisfies the doubling condition. So what I mean by a quasi-metric here is a function on this that satisfies the following conditions. So the conditions 1 and 2 here are similar to what a metric satisfies on the metric space. The last condition is called the quasi-triangle inequality. So here, instead of the triangle inequality, we introduce this constant A naught, which lies in between 1 and infinity. And we call it the quasi-triangle inequality constant. And this is how we define the quasi-metric. Coming to what a doubling condition on a measure means, we say a non-zero measure mu satisfies the doubling condition if there is a constant c mu associated to this measure, such that if we pick any point x in our set x and some radius are greater than 0 and look at the mu measure of the ball centered at x with radius 2r, this is bounded from above by c mu times mu measure of the ball centered at x with radius r. The way we define these balls, which we call the quasi-metric balls, is bxr is set of all points y in the set x such that the quasi-metric distance between x and y is less than r. So this is how we define the space of homogeneous type. And since we are dealing with the Calderon-Zygmund operators and I haven't defined them so far, I'm going to define these operators on the space of homogeneous type. So we say an operator T is a Calderon-Zygmund operator on the space of homogeneous type xt mu if T is bounded on L2 of x and has an associated kernel K that satisfies the size and the smoothness condition. So T here is a singular integral operator that is associated to this kernel K, and the K satisfies a size condition, which is for all x not equal to y, we have an upper bound on the absolute value of kxy. And we have a smoothness condition for all x, x prime, and y such that the quasi-metric distance between x and x prime is less than 1 over 2 a naught distance between x and y. This a naught is the same constant as the quasi-triangle inequality constant, and this here is the smoothness condition. In the size and the smoothness condition, we make use of this function b, which is described as the measure of the ball centered at x with radius distance of xy. And kappa that we see in the smoothness condition is called the smoothness parameter, which lies in between 0 and 1. So in order to give the main result, like the two-way inequality characterization for the Hilbert transform, we have a notion of an A2 condition and testing condition in our setting in the main result. In order to get to the A2 condition in our setting, we would make use of dyadic cubes. So there is a notion of dyadic cubes on space of homogeneous type. I wanted to state the notion of dyadic cubes on Euclidean spaces and understand the notion on space of homogeneous type as an analogous version. So just looking at the system of dyadic cubes on Rn, I'll describe few properties that the dyadic cubes satisfy. A dyadic cube in Rn is a product of dyadic intervals of same length. So if we fix an integer k, a dyadic cube of side length to the power of minus k is a set that looks of this form, which is like a product of these intervals. The property of these dyadic cubes is if we consider any two dyadic cubes, they're either disjoint, and if they intersect, then one is completely contained in the other. So one that is contained, we call it the dyadic child. And another property that is interesting is if we fix an integer k and look at a collection of all dyadic cubes of the side length to the power of minus k, then we can partition our space into a union of these cubes. And this is the disjoint union. So we use an analogous version of these dyadic cubes in our setting of space of homogeneous type in order to give the A2 condition, which I'm going to describe now. So on the space of homogeneous type, let us denote by this KQ alpha, a notion of the system of dyadic cubes. By L of Q, we denote the side length of a dyadic cube Q. And here we have the A2 condition. We say the pair of weights U and V satisfy the A2 condition for all cubes in the dyadic system dk for all integers k when we have the following condition, as well as the dual condition where we replace the roles of U and V that we have here. So in this condition, as described earlier, L of Q is the side length of the cube Q. And KQV that you see here is this integral, which is a new version of the Poisson integral that we introduced in our setting. There was a reason why we had to introduce a new version of the Poisson integral to give the A2 condition. It's because for some singular integral operators on the space of homogeneous type, there might be a Poisson integral, but the two-weight inequality for the Poisson integral might not give us any information about the two-weight inequality for that operator that we are looking at. So this construction of a new version of the Poisson integral was necessary to give a characterization for those operators. We also had to make use of an additional side condition to the A2 and the testing conditions in our setting, which we call the pivotal condition, and it's described here. So we assume that the equation 6 holds, as well as we assume the dual of it holds, again, where we replace the roles of U and V. So in this pivotal condition, we take the summation of this quantity phi, where phi is given in terms of this weight V and the new version of the Poisson integral we introduce. And the supremum is taken over all cubes, where Q is written in terms of the subpartitions or subcubes Si. The role of the pivotal condition in our result is that it's used to control the degeneracies that the pair of weights bring to the table. So now I'm going to state the main theorem, which gives us the set of sufficient conditions for the two-weight inequality. This is joint work with Dong, Lee, Sawyer, Wick, and Yang. And in this result, we consider a Calderon-Zygmund operator, T, with some smoothness parameter kappa. We consider the weights U and V that do not share a common point mass, and they satisfy the two-weight condition with the constant A2 and the pivotal condition with the constant nu. Then T is L to U to L to V bounded if and only if the testing conditions given by 7 and 8 hold, where 1Q is the indicator function on the cube Q. Here T star is the adjoint of our operator T. In this result, we were also able to characterize the best constant for the two-weight inequality in terms of the A2 testing and the pivotal constants. This symbol here means that there is some constant C such that N is less than C times A2 plus tau plus nu. Our results could also be extended to Hilbert space valued operators. And here I've described a little bit of the sketch of the proof that goes into this result. So very typical approach that we use here is to get to a system of dyadic cubes on a space of homogeneous type. So here we use the Heitinen and Kairima construction of cubes, where they say there is a probability space on the space of homogeneous type, and we can define a dyadic system. So we partition our space X as a union of these cubes. And then we recall the construction of car bases by Karima Lee Pereira Award. And here the construction is on LPXU. So we look at our test functions f and g, which I'll get into a little later. But for any function on these LP spaces, we can write them as this summation using the Haar functions. And in our case, since we are dealing with space of homogeneous type, here we have this notion of these dyadic children, where MQ is a symbol I use to denote the number of dyadic children of a cube Q, and we assume that this number is finite. So our goal here is to control the operator norm of T. And in order to control that, we look at the inner product TFG. And by using the notion of these Haar bases and Haar decomposition of F and G, and using the bilinearity of the inner product, we write out this inner product as this summation. Once we get to this summation, we split it into two pieces depending upon the length of these cubes Q and S. So we split that into two pieces where the length of Q is greater than the length of S, and the other piece where length of S is greater than length of Q. So in order to control this inner product, it's enough if we control these both pieces. And since these pieces are symmetric, it's enough if we control one of them and use the same method for the other. So this is the style, and we end up with all these terms. So in this flowchart, you see all the terms that we encounter. So we start with the inner product. The first split is this A11 and A12 that comes from this decomposition using the bilinearity and the Haar bases. And then we just look at one of these pieces and try to control this piece. And we split it into a number of pieces and use different arguments to control different terms. So a little bit of summary into what goes into the control part. So for controlling each of these terms described in this flowchart, we use either the A2 condition that we have described or the testing conditions and the pivotal conditions. Some of these terms that we have in this flowchart use stopping time arguments, and some use the paraproduct and the Carlson measure estimates. I haven't gone too much into the details of control of each of these terms, and I'm going to jump right now into the applications of this result. So one of the applications that we see is for the Bessel-Rees transforms. So if we consider the Bessel operator given here and look at the Bessel-Rees transform, which is given in this, it is actually a Calderon-Zygmund operator on the space of homogeneous type described by this tuple R plus with the notion of absolute value as the quasimetric and dm lambda as the doubling measure. So dm lambda of x is described as x to the power of 2 lambda dx, and our result applies and gives us a set of sufficient conditions for the two-weight inequality of this Bessel-Rees transform. There are many applications, and I've chosen to put this one here because actually we have the two-weight inequalities for the Poisson integral associated to the Bessel-Rees transform. However, the two-weight inequality for the Poisson integral does not really give us any information for this operator. So this is an example of an operator where the notion of the Poisson, the traditional notion of the Poisson integral doesn't work, and our new version of the Poisson integral is necessary to handle the characterization. Another example that I've put here is the Bergman projection. So for some f in the L2 space, for mu, which is the Lebesgue measure on Cn, the Bergman projection, which is described here as an integral operator, is a Calderon-Zygmund operator on the space of homogeneous type given by the unit ball in Cn with some pseudo distance d, and our result can be used to give the characterization for the two-weight inequality of the Bergman projection. As I said earlier, our result also extends to Hilbert space-valued operators. So for examples concerning those operators, we can look at the characterization for the Littlewood-Paley G function and the Lucent's area function with one of the Hilbert spaces, H1, being equal to the complex plane. So these are some of the applications of our results. So in the recent times, we have been looking to extend our results to bilinear Calderon-Zygmund operators. So I'm going to state so far the results that we've obtained in this direction. So just for brevity, instead of looking at multilinear Calderon-Zygmund operators, I'm going to describe everything for bilinear Calderon-Zygmund operators. I'm going to start with the definition for these. The bilinear Calderon-Zygmund operators can be realized as a family of truncation T epsilon, and they are given as these integral operators associated to the kernel KXYZ, which is a bilinear Calderon-Zygmund kernel that satisfies size and smoothness condition that can be understood as extensions to the size and smoothness condition that we described earlier. And we can also define the adjoint of these bilinear Calderon-Zygmund operators, which I'm going to denote here with T1 star and T2 star. And this is how we define the adjoint of the operator T. There's several boundedness results that we already know for the multilinear Calderon-Zygmund operators, and I'm going to start with the boundedness result that we know for the bilinear Hilbert transform on the product LP space spaces. So on LP cross LQ into LR, where P, Q, and R satisfy this kind of a Holder relation, the boundedness of the bilinear Hilbert transform was given by Lacey and Tiale. And here P and Q lie in between 1 and infinity, and R lies in between 2/3 and infinity. So this was one of the very interesting results in the bilinear setting. And we also have the notion of multilinear T of 1 theorems that were systematically provided by Grafficus and Torres, where they actually discussed the boundedness of multilinear Calderon-Zygmund operators on product LP spaces for a class of weights. They also gave one-weight non-inequalities for these operators. Coming to our question, what we are investigating right now is in the same direction as what we have for the two-weight inequalities. So what we are interested currently is to provide a characterization for the tuple of weights U1, U2, and V, so that the following norm inequality given by equation 9 holds for the bilinear Calderon-Zygmund operator T. And in this case, the only reason we have these exponents where we have L2 and L4 is because we wanted the target space to be a Hilbert space. So we worked in this setting. And more recently, we have this result which follows the same recipe as the two-weight result that we have on the space of homogeneous type. So the result is as follows for the bilinear Calderon-Zygmund operator. We consider a bilinear Calderon-Zygmund operator T with some smoothness parameter. We consider our weights U1, U2, and V. We, in this case, were only able to provide or prove our results so far on the Euclidean spaces. We haven't really tried doing it on the space of homogeneous type. So the theorem that you see here is just in the Euclidean setting. And we assume that the weights that we have do not share a common point mass, which is described by these equations. We also assume that these weights satisfy the A2 condition and the pivotal condition, which I'll show in a minute. Then we were able to show that the operator T is bounded from L4U1 cross L4U2 to L2 of V, if and only if the operator T and its adjoints T1 star and T2 star satisfied the following testing conditions. We were also able to characterize the best constant for this multi-weight inequality in terms of the constants A2, the pivotal constant, and the testing constants. So here this means the same, that n is less than some constant times A2 plus tau plus mu. And the A2 condition that we used in this setting is described here, and it can be understood as an extension of the A2 condition that we had seen earlier on the space of homogeneous type. So in this A2 condition too, we make use of a new version of Poisson integral in some sense, and that is described by K here again, and that is this integral that we use. And there's similar reasons why we had to introduce this new version in our setting to give the main result. The pivotal condition in the bilinear case also is in the same spirit as the pivotal condition that we had seen earlier, where we sum over this function phi that is given in terms of the new version of the Poisson integral. And the role of the pivotal condition here is also the same. It is used in controlling the degeneracies that these weights introduce and that come here. So, as I said earlier, we are currently working in the direction of improving this result and seeing if a similar result can be given in the setting of space of homogeneous type. And some other future goals that we have in this direction include obtaining the set of necessary and sufficient conditions for the bilinear Hilbert transform. Now, this is a very ambitious problem that we are looking at, and this would require a lot of time, but I thought I might as well mention it. So the bilinear Hilbert transform is given as this principal valued integral. Now, this is not similar to how I have described the bilinear singular integral operator or a Calderon-Zygmund operator earlier, because here we just have a singular integral. But we are currently working on looking at a variant of this result that gives us a set of sufficient conditions for the multivariate norm inequality for the bilinear Hilbert transform. And we are also interested in ideally at some point understanding if at all we could get any necessary conditions to so that this weighted norm inequality holds for the bilinear Hilbert transform. Another interesting questions that came up when I have started working in this direction include the role of the pivotal condition in our result. So in our result concerning the Calderon-Zygmund operators on spaces of homogeneous type, we make use of the pivotal side condition. And it can be seen that in the two-weight inequality for the Hilbert transform, there is the notion of the pivotal condition was actually replaced by a weaker energy condition. So it would be very fascinating to understand if a similar notion can be incorporated into our result that I described for Calderon-Zygmund operators on the space of homogeneous type. So this is another interesting question that comes up that I get asked a lot, if the pivotal condition can ever be replaced by some weaker energy type argument. I think I still have 10 minutes. So here I just stated a couple of other boundedness results that are interesting and in the same spirit. So here the result that I have is for the commutator operators. So I just stated some of the boundedness results here. And the one of the results that I stated here is if we have a locally integrable function on a space of homogeneous type and some function f, an operator t, we can define the commutator operator in this fashion. And we can talk a lot about several boundedness results of these commutator operators. And in the recent times, we have shown this very interesting result for p lying between 1 and infinity, and for smoothness parameter kappa for a Calderon-Zygmund operator t, if we have AP weight omega on space of homogeneous type, we can say that the commutator BT is bounded on weighted Moray space, which can be understood as a localized LP space, if and only if this function B is in the BMO functions. So I think I could have spoken more, but this is all I prepared. So I'll stop here. Thank you.